All right, now we talk about multivariate distribution. And by that, we're getting closer and closer to what's relevant for our course. Now, so what is that multivariate distribution? Well, it's just a fancy way to say we consider more than one random variable at the same time. Now, for example, in a discrete case, you have color crayons with both color and length randomly distributed, or marbles with also random numbers on them with different colors. Or when you throw the dice more than one times. So those are very classical examples of multivariate distribution. Multi, more than one, variate, variable. For continuous variables, for example, we could have the distribution of income and food consumption. Now we consider both income and food consumption at the same time. What else? Well, as a human being, now we deal with multivariate distribution actually at the time we born already. For example, eye color, hair colors, the shape of our lips, the shape of our nose, how tall we are, and so and so. So we are the observations, the outcomes, or the realization of a very complex multivariate distribution biologically. But also, if you look at social economic factors, also quite interesting. For example, our parents' education, how many siblings you have, the average GDP per capita of your town, like where you were born. No? These things randomly distributed, right? So these examples show that the multivariate distribution can be all discrete, like those random variables that we're considering generally can be all discrete, all continuous, or could also be a mixture of both, right? So back to here, in economics, multivariate distribution is at the core of interest. We're particularly interested in the relationship of many variables at a time and how they interact, whether they depend on each other or not, and to which extent, which cause what, and so and so and so. No? Why? Because they're all there. No? We don't have the luxury to tease out each variable to consider once at a time and to put it in a vacuum environment, so to say, like in other hard science. So you may have already an impression that OLS, ordinary listware, is actually a way to consider this relationship, jolly, right? So it's at the core of interest and why it is so important. If you don't want to say that's so relevant to learn it. No. All right, so that's the motivation. Now back here on the slide. Look, a bit more complicated, right? So the marginal, sorry, this is the wrong slide actually. I was talking about one slide I had all the time. So this is the right slide. But don't worry, we'll go back there later. No? So if we have two random variables, y and x, then we want to figure out what is the probability that y falls in a certain range, A1, B1, and x in turn fall in a certain range, A2 and B2. We have to look at the John density. So this is the continuous case, the very generic notations, but you know what to do by now. If you have discrete case, we will also do an example later. Don't worry. Now, so first you take the integrals of the distribution, the John distribution now. Integral over the range of x that we're interested in, and then in turns over the range of y. So that's why we have dx and then dy over here. So f with two letters y and x is now the John density function, so of course. So this is the case where you have only two variables considered at a time, but that can also be expanded to many more random variables case, like 3, 4, 5. Then you can just simply add integrals and then the dz, for example, at the end. Now, all right. So when we talk about multivariate or John distribution, the often impression is that they some sort of related or dependent on each other, like what we said with economic variables. Now, that's often the case. If we have a set of economic variables, at least some will be related. However, the simplest case is when we have the two independent. So independent means knowing if you have information about one, doesn't tell you anything about the other. So in this case, the same probability that we're interested in above, just simply equals the probability that y falls in this range times the probability that x falls in is A2, B2 range. Now, for one example is if you throw the dice twice and you consider only the outcome of the first time and the second time. So if the dice is fair, then the first throw and the second throw is supposed to be independent. You know, the first is, for example, 1 doesn't mean you know more about what will occur on the second time. So now let's adapt it to the density function notation. So in that case, in the continuous case, that means that you have f yx equals simply fy times fx. Therefore, this part, the integral, becomes, but let's write it, a1 y b1, a2 x b2, simply becomes the integrals from a1 to b1, then integrals from a2 to b2, fy times fx times dx times dy. But remember, only when they're independent. Otherwise, this will not ultimately equal this product. We will have an example later. Then we're back again to this slide where we have the concept of marginal distribution. So the marginal distribution, by definition, given denoted as fy, you may see that it's pretty similar to what we had before. Well, the way we had the density of y when we consider only the random variable y. Now, why is that the case? We see clearer later. Okay, for now, the marginal distribution, the density of y is given by taking the integrals of the John density function over a range of x. So this is minus infinity to plus infinity is actually the range, the distributed range of x, not y. No? So the idea here is we fix the random variables y at a certain point, a certain possible outcomes, y small y, and then we integrate all the possible outcomes of x over its distributed range. Yeah. And then we arrive in the density of y at the point y small. Small y. Yeah. So the idea here is we're given the John density of x and y, but for some reason we want to look at the distribution of y alone only, regardless of x. So in that sense, you could think about the marginal distribution as the unconditional distribution of y. Now, don't consider how it depends on x, just the distribution of y. How many colors at which frequency I have with my crayons doesn't matter how long they are. No? So there we could arrive in the expected value of y starting from the John distribution. So this is the definition of expectation that we've seen before. Now integrals over the distributed range of y. Now that's what has dy here. So minus to plus infinity is the distributed range of y. Okay? And because fy in that case is given as the marginal distribution definition above, you could just plug it in here to arrive, it becomes really ugly, to arrive in the expected value of y. So that's one way to calculate the expected value of y when you're given the John density. Okay. Now let's do one example on the board so we see that clearer. So here is one example of a multivariate distribution, in this case bivariate, two variables. So we consider a random variable y and another random variable x at the same time. To make it easier for our mind to grasp, I just make a discrete case, but yeah, try to train your mind a bit to link it back to the continuous case, okay? So now my random variable y has three outcomes, possible outcomes. Either y equals 1, 2, or 3. Similarly, my random variable x has three possible outcomes, 4, 5, or 6. All right. So let's look at this cell inside where I have some numbers in. Each of these cells is a combination of possible outcomes of x and y that may occur or may not occur. We don't know because it's random, right? Okay, and these numbers actually the probability that each specific combination will occur. For example, if let's say you have the possible combination y equal 2 and x equal 4, the probability that this specific combination occurred is 1/6, right? And similar for all 9 cells. Okay, now let's see how we can derive the marginal distribution of each variable when we're given this. First of all, the marginal probability that y equals a certain outcome y. So now if y equals 1, what is the probability that y equals 1? You sum up all the probability on this row, right? Over all possible x's. So 1/12 plus 1/12 is 2/12. 2/12 equals 1/6, right? Similar, what is the probability that y equals 2? Doesn't matter how much x is. So all the possible probability of x's when y equals 2 is 1/6, 2/6, 3/6. 3/6 is 1/2, right? Similar, for e equals 3, the probability is 2/9 plus 0 plus 1/9. That is 3/9, and that means 1/3. Now, and we could also do very similar thing when we turn our attention to x, not y anymore. So here I could write again the probability that x equals a certain small x. Again, we pay attention on the first case where small x is 4, there's possible outcomes, and we sum up all the probabilities on this columns. So 1/12, 1/6, that means 1/6, 2/12, 2/12 plus 1/12 is 3/12, plus 2/9. A bit complicated, but I give you the number. You can check it on your own. 17/36. Then we have the probability that x equals 5. You sum up this column. So 1/12 plus 1/6, 1/4. 1/12 plus 2/12, 3/12. And 3 out of 12 is 1/4, right? And then the last one would be 5/8. Now, let's use this. As similar for the univariate distribution. Back to the time we consider only y alone, or only x alone. The total probability of all possible outcomes must be 1, right? So in this case, you have a combination. So then the total probability of all the possible combinations must also account to 1. So you can check that by summing up all the probabilities in these 9 cells. It should sum up to 1. Or, as the marginal distribution is nothing else other than considering one variable at a time, like we had before. So we could actually also sum up this last row that we calculated now. 1/6 plus 1/2 plus 1/3 is 1. Or if you do it here, on this last row, sum up all the all the probability of possible x, don't care about y, then you should also have 1. So where's the marginal distribution? So the marginal distribution is this. Now, so this equal marginal distribution of y, right? And this is the marginal distribution of x. Now, what else can we do? The next thing we can do is to calculate the expectation or the expected value of y. How do we do that? Just like before, you have the probability of each outcome. You take the average of these outcomes with the probability, or here the marginal probability, being the weight, right? So the first outcome is 1 times 1/6 plus 2 times 1/2 plus 3 times 1/3. You have something like 2.17. Another thing, let's go to the previous slide where you remember we have a definition of P that you consider y smaller or equal to 2, a certain value, and x smaller or equal to 5. I just give an example here. How do you calculate that? What should you do? So in the discrete case, you simply sum up all the probability that y smaller or equal to 2. So it's until here now. And sum up all the way to the right, right? No, because we want to consider it only when x smaller or equal to 5. So only up to this point, right? So you sum up all the probability of these 2 rows over these 2 columns. That is 4 sets. And here we sum up because it's easy, we have a discrete case, but you could imagine if you have a continuous John distribution, then you take the integral instead, from minus infinity up to x equal 5, and then for y minus infinity until y equal 2. So that would be, now we sum up 1 over 12 plus another 1 over 12, that is now fix y 1, let it run, let x run from 4 to 5, right? And then the next one change, move to y equal 2, let x run again from 4 to 5. So 1/6 plus another 1/6. At the end, you have 0.5. So this is the probability that y smaller equal to and generally x smaller equal to 5. So I hope now it's clearer to you the idea of multivariate distribution and marginal distribution. This is an image of a bivariate normal distribution when you visualize it. So on one side you have the distribution of y, and then on another side you have the distribution of x. All right, and they both have the bell shape the famous bell-shaped curve of the normal distribution. So on this plane, the dotted represent the John distribution of the two. And again, just put it on an image. For example, if you want to calculate the probability that, let's say, y smaller than 2 and x is smaller than, sorry, this is minus 2 and it is also minus 2. Then you have to integrate the distribution of x until the point from minus infinity until the point minus 2 now. So you take integrals until this point. And then with that part, again take the integrals over the distributed range of y that you're interested in from minus infinity until minus 2, right? So this range. So at the end is this part, right? Yeah, that's the idea of the John density of the multivariate density. Okay, now let's talk about covariance. One thing that is very important when we talk about multivariate distribution, and is also even more relevant for econometrics. As we go deeper, you will see that this is repeated a lot in many contexts. So the covariance is a measure used to measure the linear dependency, note just linear dependency of two random variables. I will come back to this linear or nonlinear issue later. Okay, so usually is denoted as sigma xy for two random variables y and x. Or you can write it as curve y and x, which is the same for curve x and y. They're the same thing, symmetric. Then it equals the product. The product of what? The product of the deviations of the two random variables from their respective mean. So deviation of each possible outcomes in y from its mean mu y times the deviation of each possible outcomes of x from its mean mu x. And then you take the expected value or expectation of this product for all possible outcomes of the two distribution, you arrive in the covariance. We also say that y and x are uncorrelated if the covariance or this expectation equals 0. You may have heard about that already. But I show you why is the case, or like what's the implication of that shortly, but let's just finish this slide first. Then we have also the term correlation coefficient, which is derived using this covariance and the standard deviation of the two random variables. So you take the covariance divided by the product of the two standard deviations of the two random variables, you arrive in the correlation coefficients. It's called pro, usually pro xy. So why do we need that if we have the covariance already? Isn't it enough or sufficient to say something about the linear dependency already? Well, the problem is your random variables can have all kind of units, and it can take all kind of value range in which they are distributed. So when I give you a certain number, which is the value of the covariance, it's hard to judge how strongly or how weakly they are dependent or they associated with each other, right? Therefore, the correlation coefficient is useful because it always lies between -1 and 1. It's normalized in a way. So irrespective of the unit of the variables, you can always say something about how strongly they are associated. And if we have, for example, rho xy equals -1, then that's perfectly, meaning the two variable perfectly negatively correlated. Or if the correlation coefficient equal 1, then they also perfectly but positive correlated. Now that you hear sometimes already, I think. Now let's see what was the implication of the uncorrelatedness over there on the board. Okay, so this is one important thing when we talk about two uncorrelated random variables that we should remember. Also have to explain something on the slide later. So this is the definition of the covariance of the two random variables y and x on the slide. And we also denote mu y as the expected value of y and mu x as the expected value of x. So now let's use again the familiar linear operator to see what it means. Well, let me write this first. If x and y are uncorrelated, then their covariance is 0, right? Then sigma xy equals the expectation of that deviation and another deviation equals 0. And then we open the bracket inside this expectation operation. Inside we would have, no, we don't need the bracket anymore here. Okay, we would have y times x, then we would have minus mu y times x, then we again have minus mu x times y, right? And then plus mu y, mu x times each other. Curly brackets equals 0. Yeah. Then now I get rid of this sigma now. So expectation operator for linear function means that y and x minus, now because mu y is a constant, we can pull it out and take the expectation of x only. And then similar here, pull mu x out, take expectation of y itself, and because both mu are constant, no need for expectation over there, equals 0, right? Familiar thing is this is actually mu x, yeah? And this is actually mu y, right? The expectation of x and y. So then I could rewrite e yx, expectation of y times x, minus mu y times mu x, minus another mu x times mu y, which is the same thing now, plus mu y times mu x equals 0. And I simplify all the thing here. Then I would have the expectation of y times x minus only one mu y times mu x left equals 0, and that is equivalent to put the 2 mu times each other to the right hand side. And rewrite it again using the expectation notation. So that is okay, and this is important to remember. As with the case of the variance, with covariance we also have some useful or relevant rules. And some of these we will see when we talk, for example, about the properties of the OS estimator, other estimators even, and some even have a wider application somewhere else. So the first thing is, if you have two linear functions up to random variable respectively, for example here a y time plus b and cx plus d, and with a, b, c, d is constant, then the covariance of these two linear functions will equals AC, the two slope of the functions, right, times the covariance of the two random variables themselves. So the way to prove it is pretty similar to the way we proved some of the variance rules. You could try it out. We don't have to do it here. However, the second thing is, if you have a linear combination of the two random variables, some random variables y times a constant plus another random variables x times another constant, so a linear combination. Then the covariance of this linear combination with one of these random variables will depend on both the covariance of the two random variables itself and the variance of the other random variables that we're talking about now, the x in this case. So because a, b are constant, you can just pull them out, and then at the end you have this result. Then the third one is actually a very interesting property that used a lot in finance, for example, with portfolio management. So can think about y and x as the two financial assets, stock, securities, for example, and a and b are the share of them in the portfolio. Then the variance, we're talking about a variance now, of this portfolio as a whole will be decomposed into to three parts. The first two parts are the variance of the two random variables to access returns themselves. Here we're talking about returns now, the profit, so to say. And then also depends on the covariance of the two returns. Now, therefore, in this case, when we talk about the variance of the portfolio, we talk about what is the range, right? How is the range that the portfolio returns can spread? And imagine it's like this. You don't want to end up somewhere on the left tail of the returns portfolio, like the mean is 0. Yeah? So you don't want to end up there, very, very negative, like the black swan, so to say, extreme event. Yeah? And therefore, we want to reduce the risk. You reduce the variance of this portfolio. By that, usually they will try to find assets that negatively correlated, meaning the covariance of X and Y are negative. And then because its term is negative and the first two terms positive, that will reduce the variance of the returns probability distribution. Okay. Then we come to the term conditional distribution, which is highly relevant in econometrics actually. Why? Because we often interested in what the outcome of one variable. If we know the value that another variable, which may be the determinant of the interested variable, can take a certain value. For example, if we want to evaluate the impact of a policy, for example. So the impact of the policy in this case is the random variables, let's say Y. And by adjusting some other variables, X, for example, tax or something, then we would like to know the conditional distributions, how each possible outcomes in Y is likely given the fact that the tax rate is at this small x value. So for that, we have the conditional probability density functions, now denoted as again the small f as before, but inside the bracket we have the small y with a bar. This bar usually means conditional upon something. X equal a certain outcome, small x, or shortly f, small f and small y bar, small x inside, means the same thing. So you can infer this conditional density function by dividing the John density of the two random variables by the density function of X. So that's very similar to the conditional probability or the Bayes rules that you have seen in the last semester in the quantitative method class, okay? So using this, ultimately, when you cross multiply fx, the density of x, to the left-hand side, then you have the John density of x and y will equals the conditional density of y conditional on x times the density of x, the marginal density of x itself. And because it's symmetric in a way, it will also be equivalent to the product of the John density, sorry, not the John, but the conditional density of x upon y times the density of y. itself. So this is something that sometimes we will see during the course. And if we have the density function, the conditional ones, meaning we have the conditional distributions, we can also calculate the conditional expectation of y, given that we observe x at a certain outcome, okay? So nothing new compared to before with the notation or the definition of expectation now. So it's still the weighted average of all possible outcomes of y. However, the only thing changed now is the weight. We don't use the density of y itself anymore, but the conditional density of y upon x. So we use a different distribution, so to say, now for the conditional expectation. Then it comes to the conditional variance. Again, not really strange compared to what we looked before for the univariate case. You also have the variance, which is the integral over all possible outcomes of y from minus the expectation. So the deviation, the square deviation of y from the mean. However, now what changes is we use the different expectation. So it's the conditional expectation. It's not the unconditional anymore. It's the conditional expectation of y upon knowing x, right? And we also use the conditional density. And you can prove similar to what we have proven with the normal, the unconditional variance to arrive in this result. So nothing really new here. And this term conditional variance, we will see in more specific way when we come to the part with heteroscedasticity. Then it's also important to distinguish the different levels of uncorrelatedness, so to say, in statistics. Now, the first case we just seen before, x and y and x are uncorrelated. Now, and y here, that means the expectation of y times x equals the covariance y and x equals 0. So this what we knew already before. Now we show, we knew that the covariance will be 0 in this case. But why the expectation of y and x is also 0? Because of this assumption. Now, so why we have the assumption that expectation of y is 0 here? Because we want to bring it a bit closer, prepare for the next couple of weeks with OLS already. And its relationship with the implication for the residuals of the regression. So try to think about the regression residual now when we talk about the 0 expectation. Okay, so the point, here we are still here is that we know that when it's uncorrelated, then the covariance is 0, right? Meaning the expectation of y times x equals the expectation of y times the expectation of x separately. And because now we talking about a case where expectation of y is 0, here, then the right-hand side for sure must be 0. And in this case, it implies that the left-hand side must also be 0. And that's why E of y times x is 0 here on this line. The second thing, the second level is conditional mean independent. So y is conditional mean independent of x if the expectation or the conditional expectation or conditional expected value of y upon knowing x equals the expectation of y itself, and in this case particular equals 0. So it's not always equals 0, but because here we assume the expected value of y equals 0. So when we talk about OS, you will see this is very relevant for the residual again, because at some point, one important assumption that we learn is the expected value of the residual, which is 0, will equals the conditional expected value of it upon the dependent variables. You will see next week or the week after. And the interpretation for this is, doesn't matter which value x take on, it will not affect the expected value or the mean of y. So knowing which outcome x takes will not tell you anything about the expected value of y. That's the idea. And it is stronger than the earlier level, which is uncorrelated. Why? Because it implies that any combination of x will also not tell you anything about the expectation of y, even those nonlinear function of x. So because we talk about correlation as the linear dependence only, not nonlinear. So in this second case of the conditional mean independence also encompass this nonlinear function. Not only just a linear combination of x, but any nonlinear combination of x will not tell you anything systematically about the variables y of interest. And then the strongest level of uncorrelatedness is independence. So it sort of implies that any possible combination of y, either linear or nonlinear, and any possible combination of x function, so to say, either linear or nonlinear, will be independent from one another. Knowing something about one or the distribution of one will not tell you anything about the other. So for example, knowing what my parents' level of education will not tell something about your parents' education, because that's dependent, at least I hope. So in that case, the expected value of the product of the two functions here would just simply be the expected value of each function times each other. So the idea is also similar to the concept of independent that we learned before. Now, in the R file that I uploaded for the first intro session, you will also see an example of linear correlation coefficients. So this gives you the way to calculate the variance, covariance, and correlation coefficient of two random variables, presumably. However, look at how we define x and y here. So x now not random at all because it's just a range of integers number. I know every element in that before I press Control Enter, right? So it's not a random variable. As a consequence, y is also not the random variable. However, even so, you may see that the correlation coefficient of x and y is smaller than 1, even though you can calculate exactly one from the other. You can calculate y exactly if you know x. No deviation, no error, no residuals over there. It's just one mapped directly to the other, but the correlation coefficients will not be 1. Why? Because again, correlation coefficients or covariance just measure the linear dependency of the two variables. Now, in this case, these two series not linearly related. So the quadratic functions is something obviously nonlinear, right? So therefore, the correlation coefficient or the covariance is not perfect, not 1, neither -1, okay? So you can check it out yourself.